Ladies and gentlemen, up next on the main stage, we have Calvin presenting Utreexo. Enjoy.
Hello, everyone. Lovely to see your faces. So I named the talk Utreexo. You could prune my coins from your node. So you could literally prune mine coins from your node, but I'll get into that. But before we start, I'm sort of trying to see how much I have to shill it or how much I want to explain it. So do you know what Utreexo does, or like do you already know? All right, like a good amount of people. Okay, so let's get started. So agenda for today, I will shill and then explain. The main shilling points are that it's like smaller nodes and some performance wins. I'll also get into what the trade-offs are and how we deploy and what I think about it. And that's in the aligning incentives. And we'll finally get into how it works. So smaller full nodes. This is my full node. I just took a screen cap of it. And over here, of course, is the blocks folder. And this is where all your blocks live. So this is a prune node. So I'm able to prune all these blocks up until 2 days ago. And then we have the chain state. It's like 7.4 gigs now. And so this chain state is something that we really can't prune. And so the UTXO set lives in the chain state. And I think we could just skip over it. But transaction output, TXO. Here's a typical transaction. And then you have these outputs of a transaction, which is called the transaction outputs. And then you have a set of them. So all of them combined is just the UTXO set. So the UTXO set is just the combination of all the transaction outputs, and these are the actual Bitcoins you're able to spend. So UTXO set is unprunable for now. So you need to keep that. So the previous slide that I showed where it has 7.4 gigs of chain state, you can't prune that. You have to keep that. So as it grows, and it does grow, and as you could see, it's growing rather exponentially. So it's able to grow as much as the block sizes are. So we could grow 10, like 2 megabytes, I think, around in 10 minutes. So the idea, the basic idea, is to turn the UTXO set into a Merkle tree. It's not just a Merkle tree; it's like a fancy Merkle tree. That's how I sell it to people. So I like this meme where it says Merkle trees, and Utreexo is a fancy Merkle tree. But so why Merkleize it? So if we Merkleize it, then we're able to put a bound to the UTXO set growth. So we saw just with the graph, we saw like this exponential growth, but now we're able to put a bound on that. So this is another meme that I showed to explain Utreexo. So it's like without Utreexo, you have a big book, but with Utreexo, you have a small book. But because it's a constant size, even if the book grows, when your book grows without the Utreexo, with Utreexo, your book remains constant. So even if it grows a lot bigger, then you're still able to have that small size. So so it takes O of n, which is the n is the number of all UTXOs ever, and well, all the UTXOs in the current chain state, and then you're able to turn that into log 2 of n. So it's very small. So this is sort of an assumption, and these are I guess the best numbers that you could have. But if you have 8 billion UTXOs, so just one UTXO per person, then you'll have something about 472 gigabytes. Then if you take that, and if you have that as a Utreexo thing, then you'll have 416 bytes. So a lot of size savings. So this is one of the things that's in the long run, you do need it for Bitcoin because, hey, we have a Prune node, but the Prune node is still 400 gigabytes. So with Utreexo, it becomes manageable. So that's the small nodes, and there's some performance wins that actually come from these small nodes. So one of the big performance wins is that it has the same performance whether it's on a hard disk drive or SSD. And the whole reason for this is because you're just avoiding disk I/O. The chain state is currently just a key value database with level DB, and we don't have random reads anymore with Utreexo. So like, okay, so I get it, so prove it. And so what I did was I was doing IVD, and it was comparing the performance degradation running on an SSD versus a hard disk drive. So prune nodes have to flush a lot more because when you're pruning, you also have to flush the UTXO set, and so this forces this GIO to happen. 36% slower for current Bitcoin Core nodes. So this is my test methodology was, hey, I run this IBD on an NVMe SSD, and then I'll run it again on a hard disk drive. So when we done that, on a hard disk drive, it was 36% slower. With Utreexo nodes, it's about 3% slower. And this is due to some block index flushes that are happening, which it is actually possible to not even have those. And so it's a lot of savings in disk I/O, and so even if you have a really cheap disk, like a really slow hard disk drive, you're able to maintain that same speed. And because you're not writing as much, if you're running on a Raspberry Pi and say you have a micro SD card, that SD card will last a lot longer for you. So this is exactly what we flush for Utreexo. This is just in Go, and it's just a lot of roots, the block height, the roots and the number of leaves there are. So what we see here on the screen, we actually serialize that, and this is what we write to the disk. The next thing that I sort of want to shill is the parallel block validation. So the current block validation, it has to happen sequentially. So we go from block 0, and then 1, and then 2. And then so on and so forth until we reach the tip. It's like 800,000. But with parallel block validation, what we do is, the idea is sort of like assume UTXO, where you have a UTXO set, but because the UTXO set is just a Utreexo roots, we're able to commit that into the binary directly. And we're able to process any blocks that are after that UTXO set. So with Utreexo, it doesn't have to be sequential. So if we have the roots at 100,000 and 200,000, and these are untrusted roots at the start. So these come with the binary, but we don't necessarily have to trust it because we'll verify that it actually matches up. So if we sync, then we sync block 1 at the same time. We also validate block 100,001 and 200,001, and so on and so forth until we get to the block 100,000 and 200,000 and 300,000. So from here, what we do is we compare the roots at the one that we had at the beginning and the one that we calculated. And so if they're same, that means it's trusted. If they're different, that means we know our binary was wrong. So we just stop, we crash. And then we do the same exact thing for block 200,000. We look at the roots, we compare it. If they're the same, great, we saved a lot of time because we're able to parallelly validate the blocks ranges 200,000 to 300,000. So this all results in about 62% faster IBD in my testing. This was about 2 years ago, and so the numbers may have changed, but this is the rough sort of numbers that we have. Another fun thing that we could do is, because it's just parallel, we don't even have to do it on the same computer necessarily. And so the idea was that we'll have a sort of a coordinator, and that will send off work to other computers so those blocks can be validated. And I did this with a desktop and a laptop that I had, and it's about 2x faster when using 2 computers for IBD versus 1 computer for IBD. And this is the graph that I have, and if you see machine 1, that took about 426 minutes versus Bitcoin Core version 21 at 382 minutes. And if we use 2 computers, it's like about half the time. So it was able to do the IBD about twice as fast. So this is sort of a shit posting that I have. But so how much can you parallelize? And how much can you parallelize based on the Amdahl's law is, you can only parallelize what is able to be parallelly validated. If there's something that has to be done in sequence, then that can't be sped up using more computers. But a lot of it can be used. So there's very little. It's really just the block header download that can't be parallelized. So if you keep adding computers, it keeps getting faster. So presumably, if we added in the previous slides here, if we have 3 computers, we'll be 3x faster. If we have 4 computers, we'll be 4x faster. If we have 5 computers, so on and so forth. So what's the catch? It's great. It's small. You could use a SSD and a hard drive, and it'll be about the same performance. You could do this weird fancy validation stuff. What's the catch? The catch is that you have more data download. So a Utreexo node also has to download the Merkle proofs, and those proofs take up a little bit of space. So as of block 771,000, it's about 364 gigs. So I think at 700,000 was about 400 gigs. So it's about 1x, about 200 times more that you would have to download during IPD. For transaction, when you're doing like mempool stuff and when you get a transaction, that transaction will also have a Merkle proof attached to it. When you do that, it's about 4x. So typical transaction being 200 to 300 kilobytes, you'll be downloading about 800 kilobytes. There are some optimizations that are being explored that we haven't really got to now, and those optimizations just caching. So if we cache some of the proof that we have, then we're trading off memory usage for bandwidth savings. So there are optimizations being explored. So this is the sort of the meme that I give when I explain it to people. You're increasing your bandwidth a bit. I don't think it's an insignificant amount of change in your bandwidth. And your CPU, you're doing more hashes, but I also think that's sort of insignificant. And you're saving a lot in disk I/O and RAM usage. You're saving a lot. And this allows, as you've seen before, all these efficiency gains. Okay, those actually play. So deployment, how do we actually get this into people? It's 100% optional. It's 100% optional. So you could just ignore it if you don't want it. And if you want it, you could run it. But there's absolutely zero forks. So no drama anywhere to be seen with Utreexo. So these bridge nodes, so how do we do it without a soft fork? We use something called bridge nodes. And these bridge nodes will generate proofs for new blocks and transactions. And these bridge nodes have to keep the entire Merkle forest and the entire UTXO set. But these can be pruned, and we have an implementation right now, and it's implemented as an indexer at that link. What's also being developed at the moment is we have a separate binary that connects to Bitcoin Core, and that will be a bridge node. So it doesn't necessarily have to be part of a full node implementation as well. So aligning incentives is something that I really felt that it was exciting. And right now, there is no burden of UTXO storage for an individual. So when you create a transaction, you're making, if it's like a 1 and 2 outs, you're making 2 UTXOs. And there is no burden of storage for you. There is the burden of transaction fees to make that UTXO, but besides that, there is no burden anymore. So we have all these companies like Coinbase and like Binance, and because there is no burden of storage, we have like these like stamps, and you want JPEGs in your UTXO set, and that's the whole point. It's like, you store my JPEG, and you will store it for me. And so what Utreexo does is it switches the burden to everyone storing every UTXO and every coin to each storing their own. So with Utreexo, my coins are in the UTXO set, but you could prune those away for your node. So I kind of like this in that it helps this incentive where right now, if you have enough transaction fees, then it really doesn't matter in the sense that, hey, like I don't have to store it, like other people can store it for me, but now you also have to store it for yourself. And so it increases the cost of creating more UTXOs, which is beneficial for the entire network as a whole. So finally, how does it work? Algorithms, consensus algorithms. So add a UTXO, delete a UTXO, and prove that the UTXO actually exists. So going through add a UTXO. Just raise of hands if you know how Merkle trees work. Like, do we know Merkle trees? All right, quite a few of you. Okay, so we'll do this quick. So if you have 4 things to hash, if you have 4 elements in the set, so let's say we have A, B, C, and D. And this could be UTXO A, B, C, and D, or just anything. So it could be like 4 messages. It's like, okay, like Alice has like 5 Bitcoins, Bob has 2 Bitcoins. It could be anything, and you would hash it. And we hash each of the pairs, so A and B go together. So we put A, B, and we put it through a hash function, and that becomes E. Same thing with C and D, and that becomes F. until we have 1 left, and that's the root. So this is how a normal Merkle tree construction would work. With Utreexo, it's a little bit different. So if you have just 1 element, then that's the root. You just have that one, that's single root. If you have 2 UTXOs, you concatenate them. The same thing you would do with the normal Merkle tree construction. You would put them together, hash it to create a new root. So if you have two elements in the set, then your tree would look like so. And those 2 elements that you just hashed, they could be thrown away. So you don't need to keep them anywhere. You just keep the roots. So if you have 2 UTXOs, what you're actually storing looks like so. It's just 1 root. But if we have 3 UTXOs, so what it differs from a normal Merkle tree construction is that you're able to add more elements even if you only keep the roots. So if you have 3, then you just add on another one, and that becomes its own root because we don't have anything to hash with. If we have 4, yeah, it becomes its own root. If we have 4, then we add it, and because we have something that it could hash with, we concatenate, hash, and then throw away the leaves, and then now we have these 2 that we could hash together, concatenate, hash, throw away, and then we have 1 root left. Same thing with 5. 5, we don't have anything we could hash with, so we just stick it on the side. 6, now we have something to hash with, and then throw away the leaves, and then now we have 2 roots. If we have 7, then we don't have anything it could hash with, and so it becomes its own root. So we have 3 roots that we're saving. If it's 8, then now finally we have something we could hash with. Concatenate, hash, move up, delete, concatenate, hash, delete, and then we have a pair that we could hash. Now concatenate, hash, delete. Now we have 1 root. So this is how the data structure would look like, but you would only keep the root. And so that's the addition. Addition's pretty simple. It's also the same exact algorithm that's used in Blake 3 hashing. So it's not completely new, and it's been battle tested. So deletion and verification. Deletion happens with verifying the existence. So thankfully with Bitcoin, you don't just randomly delete things. When you're deleting, you also have to sort of see that it actually exists, because we're not. So when you're spending a coin, you're like, oh yeah, this coin actually exists, and now because we spend it, we delete it. So Merkle tree prove overview. So if you're proving A, remember with Merkle trees, you just need to keep the roots. Someone gives you the proof of B and F, and then you fetch A, you hash the E, then you get the roots, then you compare the root with the root that you have, and if they're the same, the proof is valid. If they're different, the proof is invalid. So this is about the same as how the proving is the same, and deletion's a little different because deletion is novel with Utreexo, at least with hash-based accumulators. So deleting A. The only requirement is that you keep the roots. So if you have the root, you can do deletion of any element. And someone will, when you're deleting A, someone will actually provide the proof for you. And in this case, if it's in a block, you will get it from the proof that comes with the block. So you calculate A from the Bitcoin block. You receive the proofs for A, which is B, J, and N. And then as you would have done with the normal Merkle tree, you hash it up to I, you get M, and then you get the root. And once you have the root, you compare it with the one that you already saved. If they're equal, then okay, yeah, I am now confident that A actually exists in the set. But if they're different, then the peer lied to you and just banned the peer. So calculate the root after deletion is, because you're deleting A, you move B up to I. And that's it, that's deletion. And since we move B up to I, we delete the old A and B. Now we hash again because M is now a hash of B and J and not I and J. And then we recalculate the root as well. And then once we have the root, we copy that root over to be saved. And that's it, that's finished. That's just deletions. So, so after deleting A, this is what your tree would look like. And it's just now you have, instead of 8 elements, now you have 7 elements, but your tree is now imbalanced and it looks like that. So if we're deleting, we have some fancy stuff for batching deletions. So if you're deleting not a single element, but if you're deleting multiple elements, then it's a little different. And if you have batch deletions, then again, you start off with the root. You get E, F, G, and H from the block, Bitcoin block, because that's what you're deleting. and then you receive the proof. And the proof is a lot smaller because you're deleting a bunch of things at the same time. You calculate k and l, calculate n, get the root, compare with the root that you already have saved, and if they're the same, then you're confident that it actually exists. Then when you're actually deleting, then now you have to calculate the new root. Since E, F, G, and H is all being deleted, it actually means that K and L is being deleted, because those are just concatenated and hashed versions of E, F, and G, and H. So remove old nodes for E, F, G, and H. After that, we're deleting N. And now, since we're deleting N, we move M up to the root, and we copy M over to be saved. And that's it. And so after deleting all those 4 elements, now we have, since we started off with 8, and now we deleted 5, so we have now 3 elements in the Merkle tree, and that's what it looks like. And that's it. That's it for consensus. So that's implemented in 174 lines of Python, if you're interested. And it's in that repo. And that's it for consensus. Those are my slides. There's a lot of links in the slides. For the deletion algorithms, I have a GIS that you could look at, which provides the actual source code to do the same exact thing. So I encourage you guys to take a look if you're curious and interested. And that's it for my talk, and I'll take some questions. I think we have like 4 minutes. I just shout it out loud, I guess. Right. Right. So ordering is important, and you only modify the tree on every block. And in that block, there's the natural ordering of the transactions, and that's the order that we go off of. Does that answer your question? Okay. Yeah, shout out. So short answer, no. But there are some properties of the trees that we're relying on, and there's some fancy stuff that we're doing that still keeps those properties that we use. And so, long story short, no, it's the same. But yeah. Oh, so the thing that's different from the original Utreexo paper is the deletions are different. In the original paper, if you look at the appendix, it'll show you how batch deletions work and how in the original paper, you would swap elements. So you would swap the deleted leaves out with the new leaves that are being added. And we're not doing that anymore because you would get bigger proofs with Bitcoin stuff, and it was less efficient in terms of performance. So we're now doing this like moving up kind of algorithm, and it's both faster and it has proof size savings. So if you don't have any bridge nodes on the network, yeah, it doesn't work. But I will mention that the bridge nodes are only responsible for generating proofs for new blocks and new transactions. Once those are propagated, they're saved with the just the normal Utreexo nodes that only keep the roots, and they're able to, they can be an archival Utreexo node. So Utreexo only affects the chain state. So you can still choose to have historical blocks and proofs for those historical blocks. And for the mempool transactions, you keep the proof along with the transaction in your mempool. So you could do it with the soft fork, and that would be a way to do it with the soft fork, and you would just force the miners to generate the proofs. But we We wanted to stay away from softworks. So there's like, yeah, just shout it out. Yep. Right. Just for the sake of the presentation, I did 100,000 blocks. For the actual testing that I showed you for the faster IBD, the increments were 1,000 blocks. But what we really want to do is do single increments, so you could verify any single block in the entire IBD. So that's the current goal. But the implementation.
For further questions, can you please come to the front?
There's no reason. We just for the sake of the presentation.
Yeah, this type of system, of course, has the property that wallets can potentially store, the partial proofs required for spending. Have you actually tried like prototyping any of that to just see what that would look like?
Yeah, the wallet is actually all implemented, and it's in that repo of like the Github organization Utreexo. It's under Utreexo-D, and we've implemented it as the wallet has a state, and then using that state, we're able to support the Electrum protocol. So it essentially acts as an Electrum personal server, and when you start up your node, you just give it your master public key, and it will scan and look for your own UTXOs that you control, and it will update those proofs as you go.
Cool.
Is that it?
If no further questions, thank you to Calvin.
All right. Hopefully I shilled Utreexo.